Before the takeoff, there's silence. Not inside the aircraft, but in the minds of those who engineered its mission. A Boeing 747F, designed to carry tons of industrial cargo, is now prepared to carry something entirely different. Life. Not just any life, but athletes in their prime. Nervous, valuable, irreplaceable. Horses bred and trained for Olympic competition. Each one weighing over 1,200 kilograms. Each one representing a national investment of up to $15 million. And each one about to board a flying stable designed with the same engineering principles used in satellite launch capsules. From the outside, it's just another cargo operation. But behind the reinforced doors of this aircraft lies an invisible challenge: how to transport prey animals, built for flight and sensitive to the slightest stress, through the stratosphere, immobilized for over 14 hours, without compromising their performance, health, or value. This isn't just logistics. It's neurobiology, climate control, engineering, and behavioral science, all operating in synchronized precision, like the gears of a finely tuned mechanism. And when the cargo is alive, the margin for error becomes smaller than a heartbeat. The technical challenge begins long before the horses set foot on the loading ramp. Inside the cargo bay, the air must circulate without creating pressure zones. The temperature must remain constant, but not static. Vibrations need to be absorbed at the level of the stall floor, not just muffled. Any unnecessary movement, any sound outside the animal's comfort range can trigger a cascade of hormonal stress that no post-flight warm-up will undo. The equine muscle, trained to Olympic response times, reacts not just to training but to trauma. In other words, performance begins in the cargo hold. To understand the scale of planning involved, imagine this: a single national team might fly with 6 to 10 horses. Each one occupies an individual stall, built to allow limited movement without risk of injury. Together, they require a modular cargo space of around 60 square meters, carefully zoned for airflow, humidity, and light exposure. These aren't cages. They are dynamic containment systems equipped with floor shock absorbers, reinforced walls, and internal climate partitions. And they're not adapted from standard animal transport. They're adapted from aerospace engineering, the same kind of vibration isolation logic used to protect satellites during launch. Each horse is loaded in silence, guided by familiar handlers, and surrounded by controlled stimuli. From this moment forward, everything becomes a balance between containment and comfort, between biological need and logistical efficiency. Specialized ramps minimize joint pressure. Air filters regulate oxygen content. Sensors monitor temperature, CO2 levels, and even posture. This is not a matter of luxury. It's a matter of muscle chemistry, metabolic equilibrium, and mental state. The aircraft itself becomes a biomechanical ecosystem in motion, and inside it, the horse is both cargo and passenger, both athlete and equation. But there is a contradiction that technology still struggles to solve. How do you maintain the readiness of an animal hardwired for fear? Inside a flying container, it cannot escape. The body remains still. The mind does not. And this internal tension, if not controlled, unravels everything that came before. Years of training, thousands of kilometers of preparation, millions of dollars of investment. In Olympic horse transport, success isn't just measured by arrival. It's measured by how much of the animal's potential survives the journey. Now, the engines roar, and one by one, the stables rise into the belly of the plane. On the outside, it's just another takeoff. But inside those aluminum walls, lies one of the most complex intersections between biology and logistics the modern world has ever built. This is the invisible infrastructure behind equestrian air freight. This is the technology that moves muscle, memory, and mental hopes through the sky. There's a moment, barely perceptible, when the horse shifts its weight inside the stall. It's not physical discomfort, it's neurological overload. Before the plane even leaves the ground, something subtle yet decisive has begun. A rise in cortisol, triggered by frequencies the human ear barely registers. In cargo hangars, where turbines hum and hydraulic systems operate without pause, horses are bombarded by sound peaks above 8 kHz. To them, this isn't background noise. It's perceived threat, and the body reacts as it has for millennia, with stress. This stress doesn't explode outward. It seeps inward, silently or altering the animal's metabolism. Cortisol triggers changes in blood chemistry, muscular tension, hydration levels. The horse appears calm, but its system is already compensating for something it cannot understand. And the consequence of this begins hours later, mid-flight or even on landing, when oxygen absorption drops, lactate recovery slows, and muscle responsiveness falters. The performance wasn't lost on the field. It was lost in the air, long before the first jump. That's why modern Olympic stalls are not simply containers. They are controlled acoustic environments, inspired by an unlikely source: hydroelectric turbine enclosures. The same panels used to reduce vibration and noise in power plants have been adapted for mobile use, forming a sound-absorbing shell that reduces auditory stress by up to 60%, without any need for sedation. The difference is dramatic. Horses transported in these conditions arrive with lower cortisol levels, higher oxygen saturation, and faster return to baseline performance metrics. Paradoxically, sedation, long considered a practical solution, is now seen as counterproductive. Sedated horses might remain motionless during flight, but studies show a clear drop in post-flight recovery. Their blood oxygenation is consistently lower. Their behavior on arrival is dull, slow to respond. In contrast, animals transported using environmental modulation, regulated light, filtered sound, structured movement, retain not just physical health, but competitive readiness. The solution is no longer chemical, it's sensory. During the Tokyo 2021 Olympic cycle, the Dutch equestrian team implemented dynamic light stabling for the transcontinental leg. The lighting, spectrum adjusted to simulate circadian rhythm, helped maintain hormonal balance and internal clock alignment during flight. The result was measurable: improved response times during warm-up, reduced fatigue indicators, and more consistent performance from day one. What might seem like a detail, light spectrum in flight, became a decisive factor in elite readiness. This changes the way logistics are understood. It's not just about speed, temperature, or stability. It's about perception, about controlling what the horse sees, hears, and senses while unable to move or react. Every stimulus must be accounted for, because when performance is measured in tenths of a second, in millimeters of movement, even the smallest physiological imbalance becomes visible on the scoreboard. So the question isn't just how fast or how safely the cargo moves. It's whether your logistics system understands the neurology of the animal it transports. Because the difference between a gold medal and a missed landing can begin hours before takeoff, at the loading ramp, with a frequency no human can hear. Inside the metallic silence of a cruising aircraft, there's a hidden choreography of air, temperature, and respiration. The horse stands motionless, but its lungs continue to work with precision, exchanging oxygen, releasing carbon dioxide, adapting to altitude, pressure, and confinement. In the narrow space of a cargo stall, breathing is not just biological, it becomes architectural, and a single design flaw can turn a safe journey into a metabolic struggle. The greatest threat isn't visible. It gathers slowly, forming in the animal's immediate breathing zone, a concentration of carbon dioxide near the muzzle. As the horse exhales, warm air lingers. Without vertical airflow separation, that exhaled CO2 begins to accumulate. What begins as a subtle inefficiency soon becomes a physiological obstacle. Fatigue increases, hydration balance shifts, and the horse, still standing, begins to show signs of internal decline long before the descent. That's why airflow design is no longer treated as a comfort feature. It's a structural imperative. Drawing from innovations in poultry live haul transport, engineers have implemented bifurcated airflow shafts inside equine containers. These systems divide the air movement into upper and lower circuits, using deflection shields to redirect exhaled air downward and away from the animal's nostrils. What this creates is a clean respiratory corridor, an invisible zone of clarity in an otherwise recycled atmosphere. The difference is measurable. In traditional, non-compartmentalized containers, carbon dioxide levels can exceed 1,500 parts per million after just 6 hours in flight. In contrast, units with dual-zone airflow maintain levels consistently below 600 ppm. That gap, almost threefold, is the line between controlled respiration and progressive fatigue. And it's not theoretical. It's visible in telemetry. On a UK-Japan equine route in 2019, one aircraft was equipped with live CO2 tracking inside each stall. After 5 hours, a single unit showed abnormal readings. The cause? An internal stall gate had shifted just 3 centimeters, disrupting the airflow pattern. Within 40 minutes, carbon dioxide levels surpassed safe thresholds. The team made a decision: divert and land for emergency re-oxygenation. The maneuver cost $45,000. But the horse arrived alive, stable, and eventually competed. This kind of incident isn't a failure. It's a window into how fragile high-performance biological transport can be. When everything depends on invisible air patterns, stall geometry becomes as vital as speed or route. A floor that's too flat, a vent that's 2 degrees off axis, a gate that doesn't close with absolute precision. These are not details. They are risk factors. So the issue is no longer about air conditioning. It's about targeted respiration, mapping airflow not in cubic meters per hour, but in relation to where the horse breathes, how it exhales, and how quickly the system clears that breath from the immediate zone. Not all air is equal. Not all temperature regulation guarantees safety. Without precise environmental mapping, the system operates blind, trusting in averages, unaware of the real conditions inside the breathing corridor. In a space where the athlete cannot move, air becomes motion. It must reach, adapt, circulate with intelligence, and each component of the container, the floor grid, the ventilation shaft, the exhaust angle, must work not like accessories, but like organs of a living structure. A transport unit that doesn't just carry life, it supports it. Continuously, precisely, and invisibly. Transporting Olympic horses may appear to be a luxury, a logistical feat reserved for elite competitions. But when analyzed through the lens of agricultural engineering, it reveals something deeper, a living model of what it means to move biological systems with intelligence and precision. Every element of this operation, from airflow zones to lighting control, is designed not for convenience, but for survival under pressure. The same physiological sensitivities apply to many species across the agricultural world. Like pigs in mobile units, these horses must breathe in balanced airflows, hydrate in rhythm with flight intervals, and maintain stable metabolism under motion. The challenge is always the same: how to transport life without compromising its internal systems. This is where logistics becomes a form of applied physiology. Technologies first developed for high-value horses are already shaping broader applications. Emirates Sky Cargo, for instance, has implemented predictive livestock protocols that use real-time biometrics to adjust environmental parameters in transit, from temperature and humidity to oxygen levels and light cycles. These systems don't just respond to stress. They anticipate it. They treat transport as a biological process. This matters far beyond the Olympic arena. In the air today are genetically valuable cattle, aquaculture species with strict temperature tolerance, and breeding animals whose reproductive cycles can be disrupted by poorly managed environments. Each one depends on transport systems designed with the same attention to air, light, noise, and structure as those used for equine athletes. What equestrian freight demonstrates is that when we respect the biology of cargo, we change the meaning of logistics. The container is no longer a passive shell, it becomes an adaptive shell, one that breathes, reacts, protects, and that transforms the role of transport itself. from movement to maintenance, from transit to care, because the body of the animal doesn't forget. It registers every hour in flight, every imbalance in air pressure, every vibration that wasn't absorbed. These experiences shape not only immediate health, but long-term outcomes, from performance to reproduction to yield. A container that's 2 degrees too warm or 12 decibels too loud can erase months of preparation. This is why the horse matters, because it teaches us to listen to life in motion. Every hoof step in the air becomes a signal, a reminder that agriculture doesn't end at the gate or the port. It continues in the cargo hold, in the circuits of a refrigerated container, in the flow of air through a stall. And the more precise we become, the more invisible that system becomes, until all that remains is performance, safety, and life that arrives intact. In this way, equestrian air freight isn't an exception, it's a preview, a glimpse into the kind of logistical thinking required to sustain a global agricultural system where quality, value, and welfare move together, silently, efficiently, and with engineered grace.